Hello and welcome to this 8th session on symmetry and chemistry. We've had a bit of a break, so let's recap some of the ideas. And in fact, what we'll do is we'll actually use a different molecule to recap these ideas. We'll have a look at ammonia, which is quite an interesting molecule. You can see a picture of the molecule on the screen there. And the first thing we really need to do is to define our axes. So we're going to define the z-axis as the vertical axis. It's the axis of highest symmetry, because going through the central nitrogen atom it's going to hold all the threefold symmetry of the molecule. You can see I've numbered the hydrogens there on the slide, H1, H2 and H3. And so let's define the x-axis. So the hydrogen atom is on the x-axis. So the hydrogen-nitrogen bond will be in the xz plane. Right, so what we'll do is we'll consider the different symmetry operations, and we're going to plot them in a table where we do the row operation first and the column operation second. And so in the ammonia molecule we've got this threefold rotation. We can do it once or twice, C3, C3 twice, and we've got three mirror planes, sigma 1, sigma 2 and sigma 3. And so I've defined them so that the mirror plane sigma 1 goes through hydrogen 1 as well as obviously nitrogen. Sigma 2 goes through hydrogen 2, etc. And so as a bit of a recap, we can see how we can follow one operation by a second one and consider that as a product of two operations where we do the row one first. So for example, you can see if the row operation is E, the identity, then the combination of the two operations is just equal to the second operation there, trivially. Then again, if we look down to a slightly more involved case, if we take sigma 1, so sigma 1 there is that mirror plane holding H1 and the nitrogen. If we apply that operation, that reflection symmetry, and then let's say we follow it by a C3 rotation, and so we take these rotations to be anti-clockwise. Let's see what happens. So when you apply sigma 1, H1 stays put, H2 and H3 switch places. Then we apply the C3 operation. That puts the H1 on top of the H2. The H3, which had been flipped across to H2 by the mirror reflection, then gets rotated back onto H3. While H2, having been flipped onto H3 by the reflection, that will then rotate round into the position H1 was in originally. So you can see then that if we start with sigma 1 and then follow it by a threefold rotation, then the upshot of that is that the H3 atom overall doesn't move, but the H1 and the H2 atoms will swap place. And so that's why when you put these two operations together, sigma 1 followed by C3, that has the same overall effect as sigma 3. That's to say a reflection through the plane which holds hydrogen H3 and the nitrogen atom. And so that really takes us back to this thing as a kind of group structure, because in order to behave like a group, the product of any two operations has to be another operation in the group. And so we've seen that here with the sigma 1 followed by the C3. And then again, just looking at the table overall, we can see that if you go across any row holds all of the operations occurring just once. And then likewise, you can go down any column, and you can see any column holds all of the operations just once. And so this is a particular characteristic of these groups that we come across in the most abstract sense. Each row and each column holds every operation once. So it's a bit like a Sudoku, really. And the curious thing is that even though this is a different example to what we used before, we actually see the same kind of symmetry in action. So last time we were looking at D3, this was the kind of propeller shaped molecule, and D3 had different symmetry operations. So you might remember it didn't have any of the reflection symmetry, it just had rotation symmetries, but despite that it actually looked exactly like this, had the same structure, which is to say there were 6 operations and they multiplied by each other to form this kind of 6 by 6 table, and the orientations, the patterns if you like, of all the different symmetry operations look the same. So effectively, it was the same kind of symmetrical object, even though we view it as a different type of molecular symmetry. Now we'll recap the idea of matrix operations. And so if we consider this threefold rotation symmetry, for example, in the ammonia molecule, we can see that we can apply it once, twice or three times, and the three times being a bit of a special case, the C33, because that just returns you to where you were at the start. So doing an n-fold rotation n times is the same as the identity. And so we can create a matrix here to represent the rotation. And so if we're rotating around the z-axis here, we get the matrix shown on the screen. And you notice that in the third row and the third column, you only see the number 1. And this illustrates the fact that the z-coordinate is unaffected by the rotation around the z-axis. So it'll rotate x and y into each other's positions, but the z will stay constant. And you can see the top left 2 by 2 matrix there. This is the matrix that we saw for an anti-clockwise rotation of angle theta in the xy plane. And so in this particular case, having taken above there the general matrix for a rotation by angle theta, we can look at it at the specific cases of theta being 120, 240 and 360 degrees, corresponding to these three types of rotation around this threefold axis. And so what we see in these larger matrices now are simply inserting the angles into the cos and the sine functions. So the cos of 120 is minus a half, whereas the sine of 120 is root 3 over 2. So in that left-hand matrix there, we've just substituted the angle 120 into those trig functions. Then in the middle there, in the middle matrix, we've done the same thing, except we've inserted in 240 degrees. And so you can see there that the coses haven't been affected, but the sines have changed sign. And then on the right-hand matrix there, rather special one, where we put 360 degrees in, and so that just leaves us with this identity matrix here. And so an interesting property of these matrices is looking at the traces, and the trace is the sum of all the diagonal elements. And so you can see here that when you look at the first two matrices there of the three, these ones have got a 0 trace. So minus a half, and plus 1 add up to 0. And so they have that in common. But you notice that with the 360 degree rotation, which is the same as no rotation, this has got a trace of 3. And so in that sense, the rotation by 360 degrees really is a different kind of beast to the other two, because it's got a different character. So significantly, it's left all the atom positions unchanged, whereas in the first two examples, all of the atoms have moved. And so for that reason, they can be living in, as it were, in different symmetry classes. Now we'll have a little bit of revision of reflection matrices. And so we looked at the XZ mirror plane before, and if we consider the XZ mirror plane acting on the X, Y and Z coordinates, you can see here that the X coordinate and the Z coordinate are going to be unaffected by the XZ plane, but the Y will just be reflected across to give minus Y. And that's what we have represented in the matrix at the top there. And one thing that's quite interesting is if you rotate a reflection plane. So when you look at a matrix that represents a reflection in a mirror plane that's been rotated by an angle theta, you can see, looking at the matrix on the screen there, that we actually get 2 theta appearing in the trig functions. So if you think about it, if you rotate a mirror by an angle theta, not only is there that angle theta, but the reflected point is going to be reflected, as it were, another theta on the other side of the mirror. So you get this 2 theta coming up in the reflections of rotated mirror planes there. And so you can see, perhaps you can appreciate, just looking at this plane where we've reflected it theta degrees anti-clockwise, if you like, around the z-axis, let's say this xz plane. And so you can see here that the z coordinate is unaffected, so we've still got that 1 there. But this time the x and the y, they are going to be affected by this rotation. And so we've got this angle 2 theta in there. So you can see there with the y coordinate, it's still going to be turned into a negative coordinate by the mirror plane, but it's just got this factor 2 theta in the cos affecting it. Likewise, you see that x and y start moving into each other, so we've got these off-diagonal elements of sine 2 theta. And I think you can kind of appreciate that. So you can perhaps just looking at the screen there, if you think about the xy plane, which is in the plane of the screen, if you tilt that, if you rotate that a bit anti-clockwise, so it's sort of moving in the xy plane towards y, then what you find in this situation that x will now reflect into a new position through the mirror, and it's going to gain a bit of positive y character in the process. And likewise, when the mirror is tilted, when the y reflects in the mirror, yes, it's going to give you some minus y, but there's also going to be a bit of positive x in the reflected point as well. So that, if you like, rationalizes the signs that you see in that matrix. So the other two reflections, that's to say, because that XZ reflection, that was reflecting in the H1 atom and the nitrogen atom. Suppose we wanted to see what the matrices look like for the sigma 2 and the sigma 3, where you're holding the H2 atom or the H3 atom. Well, here are these other two matrices. And so what we've got here are essentially the 120 degrees and the 240 degrees rotations of the mirror plane, which you get going into hydrogen atom H2 and H3 because they're related by this C3 rotation axis. Then what we've done is we've just substituted the angle in. So for example, that matrix on the left there, we've done a 120 degree rotation of the mirror plane to take it from hydrogen atom H1 into atom H2. And so that 120 degree rotation, well, it says 2 theta in the formula, so these are the trig functions of 240 degrees. So the cos of 240 is minus a half, and the sine of 240 is minus root 3 over 2. Then, as far as the second matrix is concerned, we can see that that's going to be a rotation of 240 degrees, and then 2 theta is going to take that to 480 degrees. Of course, a rotation by 480 degrees is the same as a rotation by 120 degrees. So what we see there is we see the minus a half for cos 2 theta, that's the cos of 120 degrees, and the root 3 over 2 there, that's the sine of 120 degrees. And so you can see how this is all, you see the general formula for the rotated reflection plane. You can see there that that is consistent with the original matrix at the top. Because if you think about it, if you put theta equals 0 into the general expression, that gives you cos of 0 and minus cos of 0 on those two diagonal points, and the sines of 0 come out as 0. So that xz mirror plane matrix is of course consistent with our general matrix function. And just the final point to make here is that all of these matrices have a common trace of 1. So you can see that even that in the general matrix there, the cos 2 theta, the minus cos 2 theta, that'll cancel out, and that leaves you with 1 there for the trace. And these slightly more complicated examples towards the bottom, again, they all just cancel out to 1. And so this common trace of 1, I suppose, reflects the fact that one of the H atoms is staying still during this reflection process. And so now a bit of recap into these matrix operations. And so, you know, why do we even bother with matrices? And well, it turns out that if we multiply these matrices together that represent these symmetry operations, then the product matrix is the matrix for the symmetry operation product that we did in the original table that we were looking at before. So we find that these symmetry elements multiply together in the same way that the matrices that represent them multiply together. And so this table of combining symmetry operations looks just the same when you do it in terms of the matrices. So you might think, what's the point of that? But really the point of this, and this is kind of the whole point of representation theory, is that once you can get all these symmetry operations in the form of matrices, you then suddenly have all that extensive mathematics that's known about, that we know to do with matrices. We can bring that all to bear. And so then using all that matrix mathematics, we can make a lot of headway from all this theory. And so one thing we've seen already, do you remember with the 2-3-fold rotation matrices, they had the same characters. And likewise, we saw our reflection matrices, they had the same characters. And then this just reminds us of our general rule that we classify these symmetry operations into classes where all the matrices within that class have the same characters. And so character, trace, we can use that pretty much interchangeably. So the character of a matrix, when we say that, we really mean the trace of the matrix. That's to say the sum of the terms on the leading diagonal. And this sort of brings us to a wider point, and that is that all of our symmetry operations are kind of rotations, if you think about it, because we have rotations, we have improper rotations, and in fact our reflections, really these are no different to improper rotations of order 1. And also our reflection through a centre of symmetry, really that is an improper rotation of order 2. And of course the identity, that's like a proper rotation of order 1. So in a sense we can consider all of our symmetry elements to be some kind of proper or improper rotation. And it follows that considering everything as a rotation of one sort or another, any kind of rotation by theta would have an inverse of being the rotation by minus theta. And so in that sense, all of these operations and their inverses must be in the same class, because whether the rotation is by theta or by minus theta, we find for these general rotations that these cos thetas, which we have on the leading diagonal of the matrix, of course the cos of theta is the same as the cos of minus theta. And so the trace 2 cos theta will be no different to the trace of 2 cos of minus theta. So it stands to reason then that these operations and their inverses, because of course all operations must have an inverse by our theory of groups. It's one of the requirements for group behaviour. So you may remember we had the groups have to contain the identity, operations must have an inverse. These were 2 of the conditions. So it follows then that the inverse of an operation must correspond to a matrix with the same trace, the same character, and they get put in the same class, the symmetry operation and its inverse. And what I'm going to show here is looking at a different basis with these operations. So before we were looking at a generalized point, x, y, and z, how it behaved under the effect of all the symmetry operations. But rather than x, y, and z, we're now going to look at it in terms of H1, H2, and H3, the 3 hydrogen atoms in the ammonia molecule. And so again, because we've got 3 points in our basis, again, we're going to have 3 by 3 matrices that we use to describe them. And then you'll see here that because H1 and H2 and H3 conform to the symmetry of our system, we have these incredibly simple matrices, because simply the atoms are either going to stay still or they're going to move into one of the other atoms' positions. I mean, that is really by definition of what happens in a particular point group when you consider the symmetry. So we get these very simple matrices here. So we've got the do-nothing identity matrix with just 1s on the leading diagonal, which means to say that all the atoms stay put. And then you can see here with our rotation matrices, the atoms all moving into other atoms' positions. And that leads to all these off-diagonal 1s moving the atoms around. Same sort of thing with our reflections. So again, we have one of the atoms staying still, the other 2 atoms are swapping into each other's positions, giving you these off-diagonal positions, off-diagonal matrix elements. And so we can see here that we actually have the same traces on all these matrices. So we still have 3 for the identity matrix. The rotation matrices still have a 0 trace, reflecting the fact that all the atoms move, and the reflection matrices still have a 1 trace, which reflects the fact that just one atom doesn't move. Now, I thought I'd make a few general comments about the matrices we've been looking at so far, and how they are in general so-called orthogonal matrices. And in fact, we've got a general case in front of us there, the 2x2 matrix that we see by rotation, for rotation by an angle theta anticlockwise in the xy plane. And actually, when you think about it, all symmetry operations ultimately are rotations. We have proper and improper rotations. You could argue that the identity is just a proper rotation by 0 degrees. Reflection through the center is an improper rotation of order 2. You could argue that reflections are just improper rotations of order 1. So ultimately, all of our symmetry operations can be considered as rotations, and therefore it follows that the inverse operation should be the rotation by minus theta, where the main operation was the rotation by plus theta. And so in fact, using this logic, we can deduce that the inverse operation is the transpose. And we can see this by looking at this general matrix here, because when you change theta to minus theta, it makes no difference to the cos function. But when you change theta to minus theta, it changes the sign of the sine function. So you can see here that when we look at the inverse of a matrix, what it's going to end up giving us is effectively the transpose of that matrix, where the rows and the columns have been interchanged. And so in fact, this is one way of defining an orthogonal matrix, the matrix whose inverse is its transpose. And that's what we're looking at here with these symmetry operations. And in fact, a little bit more about this word orthogonal. So orthogonal kind of implies at 90 degrees to each other. So in fact, the matrix that we're looking at there, we've got 2 rows and 2 columns. And indeed, as an orthogonal matrix, it follows that if we consider the 2 row vectors, they should be orthogonal to each other. And indeed, if we consider the 2 column vectors, they should be orthogonal to each other. And so they'd be orthogonal if their dot product or their scalar product is equal to 0. So if we consider then the 2 rows in the table up here, so that if we take row 1 as a vector and multiply it by row 2, the dot product, then that'll give us cos theta sine theta minus sine theta cos theta. So of course that comes to 0, and if we do it with the 2 columns, we get exactly the same result. And so indeed the rows are indeed orthogonal to each other, and the columns are orthogonal to each other. And so again, this is where the word orthogonal really comes from. And another point to make with these matrices is the fact they have unit determinant. So as we know, for a 2x2 matrix there, the determinant will be AD minus BC. And so looking at it, that would be cos squared theta minus sine squared theta. So that's cos squared theta plus sine squared theta, which of course comes to 1. So it's got a unit determinant, and the determinant of a matrix is rather like its scale factor. And so having a unit determinant, it means if it operates on another vector, for example, it doesn't change the length of that vector. And so in not changing the length of the vector, all it's effectively doing is rotating the vector. And of course, that's what we expect with a rotation matrix like this. So it rotates vectors without changing their length. And in fact, this has a real wider significance, because in quantum mechanics, we can often consider a quantum state to behave like a vector. You can kind of picture it as a vector. We call it an eigenvector. And indeed, these matrices, and in fact we see this generally in quantum mechanics, that these matrices effectively rotate these vectors while preserving their length. And so in quantum mechanics it's done in a slightly more abstract sense. So these sort of abstract eigenvectors, they get rotated in this abstract space we call a Hilbert space, and so they're just effectively rotated through the Hilbert space with their lengths ultimately being preserved. Now we're going to look at unitary matrices. Unitary matrices are like a generalized version of orthogonal matrices, except you can have complex entries into them as well. We just had real entries into the orthogonal matrices. So if you look at the example on the screen here, the A and the B here, these are now potentially complex quantities. And so you can see that the B star, that asterisk there, that means the complex conjugate, which is to say you've changed the sign of the imaginary part of the complex quantity. And you can see we've also got these imaginary exponentials, these like phase factors, e to the I phi. So you remember with the orthogonal matrices, where we had sine and cos functions in there, ultimately, of course, those matrices had unit determinant because sine squared plus cos squared equals 1. And so we've got a similar thing here with our A's and B's, but because A and B are potentially complex, rather than just squaring them, we take the so-called square modulus, which you can see on the screen with those vertical lines. And so what we do with the square modulus there is that we're multiplying the complex quantity by its complex conjugate, which again is changing the sign of the imaginary part. And so when you multiply those two together, that will necessarily give you a real outcome. Because of course the product of a squared plus b squared, we need to be real because it's just got to be equal to 1 in this case for our unitary matrices. And so again, just to remind you, so with the orthogonal matrices, the inverse of the matrix, which was a bit like the rotation, you remember, by minus theta degrees in the general sense, this was the transpose. And this worked because the cos of minus theta was the same as cos theta, and the sine of minus theta was minus sine theta. It turned out to be the transpose of the matrix. In the case of a unitary matrix, where we've got these complex terms, it's more than just the transpose, it's the so-called complex transpose, or the conjugate transpose, I should say, where we've taken the complex conjugate of all the terms as well as transposing the rows and the columns. And so again, the reason for doing this is because ultimately the matrix multiplied by its inverse has to give the identity, and because the identity is real, we must fix it so that when the two matrices are multiplied together you get a real outcome, and that's done by taking complex conjugates. And another thing we can say is that just like we saw with the orthogonal matrices, the two rows will behave like orthogonal vectors, and the two columns will behave like orthogonal vectors as well. In the case of the unitary matrices, when we say that they're orthogonal vectors, it's not just a case of the dot product being 0, but we need to take the complex conjugate of one of the vectors for exactly the same reason we said before. So actually looking at the matrix on the screen there, if we take the two row vectors and do the dot product, we can make either of them the complex conjugate. Doesn't make any difference. Supposing we took the second row there to be the complex conjugate, then the B star would just go back to B, because of course B star means the complex conjugate of B. But if you do the complex conjugate of something twice, let's say you change the sign of the imaginary part twice, you just go back to where you started. So that second row, if we make the complex conjugate of that row, then the A star and the B star just go back to being regular A and B. And then those imaginary exponentials there, so we need to change the sign of the imaginary part. So then they then each become e to the minus I phi. So the exponent changes sign. It doesn't make any difference to the minus in front of the whole expression or not. So if we take those two rows and we look at the dot product, then essentially because the complex conjugates disappear in the second row, then in both cases we're just going to get AB times e to the minus I phi. Except in one of those cases, in the case of the first pair, we've got that minus sign, and so those two equal terms, you just have one subtracted from the other, and it makes 0. So that shows then that the two rows are orthogonal to each other once we take the complex conjugate. Likewise, those two columns, they should also give a dot product of 0. We take a complex conjugate of one of them. So for example, if we take the complex conjugate of the second one, then the B changes to B star, and the A star will change to A, and the e to the I phi will change to e to the minus I phi. So again, if we take these products, we'd have a times b star with the top terms, and then with the bottom terms, having taken the complex conjugates, it's also a times b star. Then we look at the complex exponentials. So we'd have to multiply e to the I phi by what would now be e to the minus I phi, having taken the complex conjugates. And of course, when you multiply those together, you get e to the 0, which is 1. So what we'd end up with, we just end up with those two columns multiplied together, a times b star, except one of the terms will be negative. So again, the two equal terms with one of them negative just cancels to 0. So again, we can see that the two columns there, dot product with a complex conjugate, comes to 0. So same idea. And then I finally make the point here, just demonstrating that if you multiply one of these unitary matrices by its conjugate transpose, you do get the identity. So just comparing those two matrices on the left-hand side of the equal sign, you can see there, if we look at the diagonal terms, A is turned to A asterisk, so we've taken the complex conjugate, and then the bottom right-hand one, the A star turns into A in the second matrix, and e to the I phi turns to e to the minus I phi. So again, you can just satisfy yourself that when you multiply these all out, it does give you the identity. So you can see that if we look at the multiplication to give the top right, the top left-hand 1 in the identity matrix, you'd have A times A star plus B times B star. And so this is how we defined A and B, so that the square moduluses summed together gave you 1. And then if we were to consider that, say, that bottom left 0 there, that would be the second row from the first matrix multiplied by the first column of the second. And so what we're going to get there is we're going to get, for the first term, we'd have A star B star minus e to the I phi, and then so that's the second row and the first column, and then the second term will be A star B star e to the I phi. And so you can see there that ultimately those two terms come out the same, except there's a minus sign, the first one. So again, they'll cancel out to 0. So hopefully you can satisfy yourself working through all that they do indeed give the identity matrix. Now, the great orthogonality theorem kind of underpins everything, and it's this kind of great manifestation of orthogonality. And I suppose this represents the fact that in the most abstract sense here, these objects that we're considering, ultimately they're all independent one from another, which ultimately translates into these mathematical objects all being orthogonal one to the other. And we never actually use the great orthogonality theorem in itself. What we always use are the more minor theorems which follow from it, sometimes called the little orthogonality theorems. So what I was going to spell out on this slide were the results that we use from the great orthogonality theorem that really informs all of our group theory. And so on the right hand side there, I've got them kind of codified in these sort of neat little algebraic expressions, but they need to be unpacked a bit so you can see what they really mean. So this first one, the sum of the squares of the irrep dimensions equals the order of the group. So these irreps, this is the irreducible representations. These are the irreducible matrices that we use, that we're describing all these symmetry operations. So summing the squares of the irrep dimensions equals the order of the group. And so what we have there is that capital sigma I, that means summing over, so the I there is for the irrep. So summing over all the irreps, and the L there, the L represents the dimension of the irrep. So L sub I, that is the dimension of a particular irrep I, and if we sum over all of those squares of dimensions, we get the order of the group, which is given the symbol H that we see on the right hand side there. So we can see that sort of neatly coded up in that first expression. this second expression is to do with characters, and so that's the Greek symbol chi there in the second equation. The sum of the squares of the characters of an irrep equals the order of the group. And so for a particular irrep I, so we've just got the one irrep in this case, we're not summing over I, but in this case we're summing over R. And so what the R will be here is all the symmetry operations in the group. So for every single symmetry operation in the group, if we take the character of that symmetry operation for the particular irrep, so that's chi, the character, for the particular irrep I, for the symmetry operation R, if we take that character, we square it, and we sum these squares for all the different symmetry operations, again we get the order of the group, H. Now all the irreps are mutually orthogonal. This is one of the great strengths of these orthogonality theorems. And so again, it's a bit like these matrices. If we treat it like a vector, then the dot product of any two of these vectors comes to 0. And that is actually illustrated here in the third equation. And so the crucial thing are the labels I and j in the third equation. So I and j label the different irreps. And so what we've got here is taking these two different irreps, I and j, for all the different operations, so that's moving across the row, all the different operations in the particular group. If we take, for each operation, the character of an irrep I and multiply it by the character of an irrep j, then all of those products summed up for all the operations will give 0. And so a couple of things, just a couple of extra points that are in the equation. We've also got a complex conjugate in there. And so that complex conjugate is just allowing for there being complex characters. So actually we will meet some complex characters a bit later on. So if you have a complex character, then you will need to take a complex conjugate at this point. And then the new symbol there on the right hand side of the equation is this lowercase Greek delta, ij. And this is called the Kronecker delta. And this is a kind of shorthand where what it means is that if I and j are different, if they're different irreps, then it equals 0. And if I and j are the same irrep, that's to say if I equals j, then the Kronecker delta is given the value 1. Now in this particular case, where we're saying all irreps are mutually orthogonal, that means we're taking two different irreps, I and j, and therefore the delta, the Kronecker delta, delta ij, will equal 0. So it's just making the point there that if the irreps are different, then the sums of the products of all their characters for the different operations must come to 0. And that turns out to be fantastically useful for us later on. And then going on here now, the characters of operations in the same class are identical. This is what we saw before. Remember, these are the threefold and two lots of threefold operation. Ultimately, the characters are the same. So the characters of operations in the same class are identical. That's kind of how I suppose we define the symmetry classes, and that's why they're grouped together in this way in the character tables. So it makes the character tables much neater if we group the operations into classes. And the other thing that's really neat about this is that when you group the operations into classes, it turns out that you have the same number of symmetry classes as you do irreps. So that's extremely neat. There's actually some sort of very abstract algebra behind this, but it is all ultimately sort of mathematically holds water. And so it does mean then that all these character tables, ultimately, we see them as squares, because down the number of rows is equal to the number of columns. We've got the same number of irrep rows as we've got symmetry class columns. And just finally now, looking at some of the absolute simplest possible character tables that we can have. So the smallest orders you can possibly have for a group. Now, of course, all groups have to contain the identity element. This is a requirement to see group behavior. And so actually, trivially, the smallest group you can have is a group that holds nothing but the identity element. And so it's only got one possible irreducible representation, and that's just the sort of fully symmetric irrep that we call A, which remains unchanged surprise, surprise, when you do the do nothing operation. So what you've got on the screen there is just the most trivial, most simple case of a group. And then it gets slightly more interesting when we consider the next simplest groups, groups that have got order 2. So now we've got 2 symmetry operations. Obviously one of them has to be the identity, and we've got one other operation. And so because we've got 2 different types of symmetry class here, we're going to have 2 different irreps. And so we can see now we've got these 2 by 2 arrangements for our groups. And so when we consider molecular symmetry, there are actually 3 different point groups, 3 different types of molecular symmetry, which have this order 2. They're C2, so this is just a cyclic group where you've got a 2-fold symmetry axis. There's also CS, where the only non-trivial symmetry element is just a mirror plane, so sigma H in that case. And then the other one, CI, and this is where the only non-trivial symmetry operation is reflection through the origin, the centre of inversion I. But it's interesting that when you look at these 3 groups there, they're all order 2, they've got different symmetry operations associated with them. You see that the irreps are labelled differently, but actually in terms of the ultimate structure, they've all got the same arrangement of the same numbers in the group. So in terms of a group structure, there's no difference between them, but it's just our labels that vary a bit when we consider them with molecular symmetry. And actually looking at the labels there is quite instructive. So you can see here that the A and B label there, this reflects the different behaviour under the principal axis of rotation. Where we've got a centre of symmetry, I, then we have the labels G and U, standing for Gerade and Gerade, and this is where the functions are symmetric or antisymmetric with respect to reflection through the centre of symmetry. So you can see AG, that's the most symmetric irrep there, where it's fully symmetric with respect to reflection through the origin, but AU, that label U Ungerada, shows it's antisymmetric with respect to reflection through the origin. Similarly there, with the reflection example CS, with the reflection plane, we see primes being used in the notation. So primes reflecting whether something's symmetric or antisymmetric with respect to this mirror plane, this reflection symmetry. So you can see that A prime is symmetric with respect to the sigma H mirror plane, A double prime is antisymmetric with respect to it. So interestingly, in these trivial, very, very simple order 2 groups, we're actually seeing our nomenclature rules coming up for how we label the irreducible representations.